with YouTube. Excellent. Okay, welcome everybody again. We are joined today by Yoshimi Kubota from the National Museum of Nature and Science today for the Monsoon seminar. And so again, without further ado, I don't want to spend too much time here so that Yoshimi can get to her excellent research here. And so how about you take it over here, Yoshimi, and you can tell us about monsoon proxies and how they compare with those on land and sea.
Yes, thank you, Tara. And thank you, Peter and the DBU for organizing this nice monsoon seminar. And thank you for giving me an opportunity to give a talk today. And the title of my talk today is Local and Remote Drivers of East Asia Millennial-scale Climate. And we try to compare the monsoon proxies between marine and speleothems. Before I start my presentation, I'd like to acknowledge the contributions by the collaborators. Etsuko Wakisaka, she analyzed a part of the magnesium calcium data, which I show you today. And Steve Clemens, Ann Holborn, Kinyun Lee, Martin Ziegler, Katsunori Kimoto, Keiji Horikawa, and Ryuji Tada. So what I'm talking today is based on the result from the expedition 346, Asia Monsoon expedition. So before I start talking about the paleoclimate, I'd like to explain the feature of the East Asian monsoon today. So this figure shows the East Asian monsoon region, including other Asian monsoon region. And if you look at the East Asian monsoon here, covering China, Korea, and Japan, you can see the spatial pattern of the mode of the interannual variability in rainfall. So compared to the other regions, the East Asian monsoon regions are very unique because it has a triple mode of the interannual variability in the rainfall, especially in the Yangtze River Basin here. Can you see my arrows, maybe? Okay, so yeah, here, the spatial pattern, interannual pattern, is different from north and south. This feature came from the northward migration of the monsoon belt, which is one of the other fundamental features of the East Asian submonsoon. So the top figure shows the seasonal migration of the rain belt in this East Asian monsoon region. So the monsoon rain starts from May around the South China Sea and go to the north and reach the northern limit in August. So this is the temporal pattern of the rainfall variability in the Yangtze River Basin. In black. So the black line represents the rainfall variability in Changjiang Basin. Changjiang means, the Changjiang is the another name of the Yangtze River. And and we compare this one to the East Asian summer monsoon wind intensity, which is in blue. You can see the negative correlation, which means the rain belt goes northward quickly, then the Yangtze River Basin has less precipitation and vice versa. So the precipitation in the Yangtze River Basin and the northward migration of the rain belt has a negative correlation. This is a feature of the East Asian monsoon, and this regional complex system is different from the Indian and the other monsoon regions. And from the paleoclimate proxies, there are a lot of geological archives which shows the millennial-scale variability in the East Asian regions, such as stalagmite in China and the Japan Sea sediment. And why we focus on the millennial-scale variability? Because one reason is that usually millennial-scale variability exhibit the abrupt changes. For example, some of the changes occur within a few decades, which is shorter than the human lifespan. And another reason is that the millennial scale variability often show the high amplitude, for example, more than 10 degrees Celsius, which is found in the Greenland. And in the East Asian regions, speleothem oxygen isotope record has advantage because we can apply the uranium series dating method on the speleothem record, and usually it has a high temporal resolution. Sometimes less than 100 year, which is high enough to resolve the millennial scale variability or centennial scale variability. However, Chinese speleothem 018 has a problem in terms of the interpretation. And 018 of the water is classically regarded as a tracer of the hydrology in the modern climatology. And in the similar manner, we can utilize it in the paleoclimatology. But interpretation of the speleothem 018 is changing since the first data came out. And most people believe that the 018 of the speleothem record can be interpreted as reflecting the summer monsoon rainfall, but still ongoing argument there. And a recent modeling study pointed out the fact that the factors controlling speleothem 018 may change depending on time scales. For example, especially on millennial scales, precipitation amount, which is believed to be the one of the major factor controlling the speleothem record, is not sufficient to explain the whole amplitude of the speleothem record. And the more important factor is the movement of the monsoon front during summertime, which is closely associated with the shift of the westerlies. So many people right now are aware that the climate parameters such as the temperatures and amount of precipitation are difficult to quantify using only speleothem 018 data. So based on that, one of the motivation of our study is we need a geological evidence which is robust and reliable, and from which we can get the key climate parameters such as temperature and rainfall. And this is a recent study to try to get another information from the speleothem record. And this paper tries to using the trace element of the speleothem to get the wet or dry condition information from the speleothem record. So classically, this is this bottom figure, blue line, shows the typical patterns of the speleothem routine record. And it shows that the higher values during Heinrich event 1 and Younger Dryas event, and which is interpreted as the weak summer monsoon. But trace element, multiple trace element analysis indicate that the Heinrich event 1 was maybe wet period, and also that's the Younger Dryas period as well. And this is explained by the seasonality of the rainfall in this region. So in the previous slide, I talked about the rainfall pattern, relationship between the rainfall pattern and the shift of the rain belt northward. And in this case, why the Heinrich event 1 was wet is closely related to the movement of the rain belt. And modeling studies help to understand the mechanism of the climate variation in the many regions. So I want to explain a bit about the hosting experiment at the SGM condition using the multiple models. These right figures show that the temperature response when the Atlantic meridional overtagging circulation is shutting down. Then the top panel shows the number of models simulating increasing mean annual surface air temperature. And as you can see, none of the models show that the increase in the temperature in the response of the AMOC shutdown. On the other hand, the bottom figure shows the most of the model simulated the decreasing mean annual surface air temperature. It's a hemispheric response and very consistent within the multiple models. On the other hand, for the rainfall response, the modeling results are not consistent. Some models indicates higher precipitation in the response of the AMOC shutdown, and also some of the models indicates the decreasing precipitation in response of the AMOC shutdown. So these results show that it's still difficult to reproduce the rainfall response in multiple models on millennial time scales. And this another modeling study points out the another aspect of the millennial scale variability. And this modeling study tested the climate stability in the different global climate states such as CO2 and global ice sheet. They tested the three global states, which is interglacial and mid-glacial and full glacial. So these are the temperature response of the AMOC shutdown. And they conclude that mid-glacial state is favorable to generate the climate instability on millennial scales, because in the mid-glacial state, if we test the whole thing of the less than the less amount of the fresh water input to the high latitudes of the North Atlantic, but the temperature response, hemispheric response very well. So based on these results, second motivation of our study is how do the amplitude and the duration of the millennial scale variability depends on the orbital scale changes, such as global climate states, or insulation changes. I hope that this information will contribute to predict the future climate change as well. So we focus on the temperature and rainfall reconstruction using the marine sediment in the East China Sea here. So because we have a lot of foraminifer, which is calcite test has advantages in partitioning calcite derivative into climate parameters, which is not possible, or which is not easy using the speleothem record. And we measure derivative and magnesium calcium record, and paired to these two analysis allows us to decompose the derivative into temperature and derivative water, which is closely related to the salinity and ice volumes. And we achieved 300-year time resolution for the last 400 kilo-year. And we used the surface flora of the planktic foraminifera globigerinoides rubescens strict. So let me briefly introduce the bathymetry of the East China Sea. Yeah, this is a large map, and this is the map of the East China Sea. And our core site is located here on northern edge of the Okinawa Trough. And the Yangtze River is located here, and the river mouth is here. And as you can see, East China Sea, most of the East China Sea is a shelf area whose depth is less than 100 meters. So the Okinawa Trough area is a kind of only area to get the good and continuous marine sediment record for a long time. And this is the figure showing that the modern sea surface salinity in July, and you can see the low salinity water spread from the river mouth of the Yangtze River, and it reaches the core site here. So during summer, the sea surface temperature drops to approximately 33, and increase in the wintertime to 34. And this is a schematic image of the water masses in the East China Sea. So the seawater are flowing into the East China Sea from the south, mostly come from the Kuroshio water, which is called Kuroshio subsurface water and Kuroshio water. And the water also comes from the South China Sea through the Taiwan Strait. And the freshwater contribution is not large compared to the seawater, but still the freshwater input from the Yangtze River is the main factor to decrease the sea surface salinity in the East China Sea. So we checked the whether we can get the Yangtze River discharge information from the salinity at this site. So we analyzed the instrumental salinity data from near the core site for the last roughly 50 years compared with Yangtze River discharge. And as you can see, this is a 5-year average considering the residence time of the water mass in the East China Sea. But we have a good relationship between the salinity and freshwater discharge, which means that we can get the freshwater input information from this site. And also, salinity has a correlation with the diluting of the seawater in the East China Sea. So using the foraminiferal record and using the well-established method of the paired magnesium, calcium, and oxygen isotope, we can get the past information of the diluting of seawater, which is represent the freshwater influx from the Yangtze River. And as you can see, the Yangtze River basin is here. The drainage basin covers most of the southern China, a large area of the East Asia monsoon region, and the freshwater input from the Yangtze River can be regarded as a regional rainfall changes. So let me explain from here about the site 1429 of the IODP expedition 346. So 1429 is located here at the water at the approximately 700 water depths. And this is a columnar section of the site 1429 and 1428. And they consist of hemipelagic sediment, greenish gray ooze interbedded by the ash layers. And we recovered for the 1429, 180 meters of the continuous sediment records. And the bottom of the sediment reaches the 400 kilo a year. And this is the orbital scale variability of the U1429, which is already published in Clemens et al. 2008. And orbital scale variability are discussed in this previous paper. So I would like to show just a little bit. And the oxygen isotope of the practic and the magnesium calcium records show a beautiful orbital scale variability, which has 141 to 23 cyclicities. And in order to in order to discuss the millennial-scale variability, the age model is very important. So because 1429 is located relatively close to the Chinese cave site, we take disadvantage and compare our record to Chinese speleothem record. This is the orbital scale comparison in the left figure. And on the millennial scale, they are closely matches. And to establish the fine-tune and age model in the Clemens paper, the East China Sea records of the derivative of planktic ties to the derivative of speleothem record. So then we can get the fine-tuned age model to discuss the millennial scale changes. So this is the result again for the whole period, including the orbital scale variability from the top, 1429, derivative of planktic in orange, and the Chinese speleothem derivative in blue, and derivative of water calculated by magnesium, calcium, and derivative of foraminifera, and SST. And here, I'd like to discuss the millennial scale variability. So to eliminate the orbital scale component, we high-pass filter these data to cut the orbital scale variability here. So this is a suborbital scale variability of the derivative of planktic and the derivative of water and the SST. And SCD means standard deviation, and of course the derivative of planktic has the largest standard deviation because the derivative of water and SST is the one of the component of the derivative of planktic. So next, I'd like to show you the first standard deviation, which is instability depending on the global state. So this is a plot, standard deviation plot against the sea level for this is a published data of the Chinese speleothem cave record and Greenland, and this is for the East China Sea record. So as you can see, for the Greenland temperature record, the standard deviation tend to be higher in the mid-glacial state. And for the cave record, this is not obvious compared to the Greenland record, but still the higher standard deviation in the mid-glacial states. And East China Sea has a similar trend. You can see the lower standard deviation in the full interglacial and full glacial period, but in the mid-glacial period, the standard deviation tend to be higher. So these results suggest that the climate instability in the East China Sea also tend to be higher in the mid-glacial state. So the next, I want to look at closely into the temperature and the derivative water record here. And one of the advantage of our record is we can compare directly SST and the rating of water without considering the time gap, because this is generated using the same materials. And as you can see, there are some different pattern of SST and the rating of water. And to look at in detail, we did wavelet analysis here. So this is called wavelet coherence to examine the phase and cyclicity to look at the cyclicity and phase relationship between the two records in the time and frequency spaces. So the y-axis showing the frequency, and the arrows represent the phase between the two records. So the arrows point to the right, which means 180 degrees phase difference between the two records. In this case, in our case, cooling occur simultaneously with the drying. And if the arrows points to the the right, which means there are degrees phase difference. So the cooling occurs with the wetting. And if you have the tilt arrows, meaning that rainfall slightly lags behind the temperature record. So the cooling comes first and the drying lags a bit. Well, then we look at the data in detail. And as you can see, these yellow area represent we have the high coherence. And also the arrows shows the phase relationship between the two records. So pointed to the left, showing the cooling is associated with the drying. So like for the last 100 kilo year, from the late MIS5 to the middle of MIS3, the temperature tend to be coupled with the delta orienting of water, and which interpret as the temperature drops when the rainfall decreased, which is consistent with the classic view of the millennial-scale variability in East Asia. And mostly these events are correlated with the Heinrich event, which is highlighted in the blue line here. And in the full glacial period or full interglacial period, we have less coherent between the temperature and the delta weighting record. But some of the exceptions, like here, Heinrich event 10, 9, 11, 12, we have a short period of the coherence period. And a similar trend are found in MIS 7 to 6 and also 9 to 8. So this relationship clearly shows the pattern of the SST and delta and O18 of water has a has a state dependent. Then maybe the period when the temperature and delta of water are coupled and uncoupled is maybe the climate mechanisms very different between the two periods. And also we found that in the coherence period, we found a lot of Harnick event here. So we hypothesized that maybe the North Atlantic perturbation might be linked to this pattern. So then I compare our data to the North Atlantic high latitude data of the neoglobal Codorina pachyderma abundance, relative abundance at site 983 in the North Atlantic. This is a wavelet analysis. So the yellow colors shows the high signal intensity, which means strong millennial-scale variability. So for this analysis, I also did the high-pass filter to cut the orbital scale variability here. So that this is the frequency again. And as you can see, in the North Atlantic area, when we have the coherence and the coupled between SST and water, then we have the North Atlantic strong perturbation period. So which means maybe that not only the global climate state, but also the North Atlantic millennial scale variability may be important to control the East Asian climate variability. So when we look closely into the last 100 kilo years, then we can compare directly our records with the Greenland record. So in the most of the Harnick event, we have the high derivative of water and low SSC, which means temperature decrease when the rainfall decrease. So, but this is not we can see these kind of features in the Harnick event, but not for all the Dansgaard event cycles. And also during the full glacial period, like here, the amplitude is not high as in the mid-glacial state here. And also Harnick event 1 is not clear as we can see in the mid-glacial state. And this is also the wavelet coherence result between the derivative of Plastic versus North grip of the Greenland. And because the last 100 years is well controlled by the fine-tuned age model, so yeah, we can do this kind of analysis using two records. So as you can see, the practice of the East China Sea records is the most high, shows the most highest coherent areas. And the second one is the temperature record. And it's maybe surprising that the writing of water has much less coherence with the North Greenland record, which means maybe the North Atlantic signal easy to transfer to the East Asian region in terms of the temperature, but not for the rainfall. And our study also implicate the very important aspect of the comparison between the East China Sea record and the speleothem record. So this is a comparison between the routine of water in the East China Sea with the Chinese speleothem composite record. This is also the high-pass filter, the suborbital scale variation. And for the last 200 kilo years, these data are beautifully correlated. But from here, like around 216 to 320, the speleothem record has less temporal, the lower temporal resolution. But still, East China Sea record has the high amplitude variability in this period. So in the aspect of the comparison between the East China Sea record and the speleothem record, we can maybe conclude that the speleothem record has also the information of the rainfall amount. But as you can see, the amplitude of the absolute value is not the same as the speleothem record. So then the rainfall information is recorded in the speleothem record, but not explain a whole variability of the speleothem variation. So this is the summary of my talk. Temperature and rainfall variability revealed from the East China Sea record largely asynchronous with the time when the global climate shift from interglacial to glacial periods being the notable exception. And the North Atlantic forcing is dominant during the notable this exception period, while maybe the regional variability is predominant during the full interglacial and glacial maximum. And these findings highlight the importance of both the mean global state and the magnitude of the North Atlantic variability in determining the East Asian climate. And we suggest that without the strong Atlantic forcing, the regional feedback system maybe generate the synchronous temperature and rainfall variations, maybe which is a background climate feature in East Asia. Also, our SST and deglaciati records shows a strong correlation with deglaciating of speleothem, but to a lesser extent. This indicates that both SST and deglaciating of water are essential components of the deglaciating of speleothem signal, and that the global condition such as sea level is a crucial factor affecting local rainfall variability in East Asia. And thank you.
Great, thank you so much for your presentation. So we'll allow everybody a couple of moments here to put together some questions. Although I see that we already have one question in the chat put forth by, let's see, Peter. So Peter, did you want to read out your question aloud?
Sure. Yoshimi, what I was wondering was your record, your salinity record in the East China Sea seemed to suggest that this was linked to discharge strength on the Yangtze. But I wondered if it might be more affected by the coast moving backwards and forwards towards and away from the site as the sea level goes up and down. Do you think it's really a good proxy for discharge?
Well, yeah, the migration of the shoreline, does affect the on the orbital scale. But maybe we are talking about the millennial scale. Maybe we don't have to think too much about the shoreline migration, because we are talking about short time period variation. Yeah.
Can I ask a stupid question? So, how does people often talk about this sort of teleconnections? But how does the North Atlantic affect like East Asia? I never really understood that. Or are they both being affected by something else?
Yeah. So yeah, teleconnection is possible by the wave, planetary wave, Okay. So then some model shows that the North Atlantic perturbation quickly propagate to the East Asia, like within a few decades. Yeah, but as I show you today, the temperature may be the reproducibility of the temperature response is good enough. Yeah, but rainfall variation is still needs to improve using the to understand the mechanisms by the modeling studies, because there are a lot of differences within the models. Yeah.
Thank you very much.
Anybody else have any further questions? While you're putting together some of your thoughts, I do have a short question. So Yoshimi, this might be within the umbrella of kind of North Atlantic and Northern Hemisphere teleconnections, but have you explored the variability with your record and maybe ENSO records? So El Nino Southern Oscillation records?
Not yet, but maybe you have an idea what kind of record I should compare with, because long time millennial scale record is really limited. Yeah, but I will try to look. Yeah, I will look.
Yeah, I was hoping you would say yes, or that you were working on it, just because the coherence and the resolution in your records is very cool. And so I just didn't know if maybe there was a little bit of long-term ENSO cycle stuff in there, because that could be really useful, I think, maybe. But again, maybe, I don't know.
Yeah. That's an important point. Yeah, thank you.
You're welcome. All right, anybody else have any, excuse me, burning questions for Yoshimi this afternoon, morning, evening? Well, in that case, let's put our hands together for a lovely talk for Dr. Kubota, basically giving some of preview to her research and what looks like to be, I think, a soon to be published paper as well. And
I hope so.
So thank you. And so so before you all run away, I just want to point your attention to the next talk in the seminar series, which is happening on the 16th of March. So that's 2 weeks from now. And we'll have a talk by Kana Yogashimi at that time. So again, thank you very much to our speaker for today. And I hope the rest of you have a very nice end to your day.
Thank you very much.
You're welcome. Bye, everybody.